How long have you been a postdoc for at University of Arizona?
For about 2 years now. I'm in my
Okay.
second year. Yeah.
And you like it so far?
Yeah, it's been pretty cool. I graduated 2022, so like, a little bit after the
Right.
pandemic. So I hadn't visited. So I was like, the desert,
Mm-hmm.
is it just gonna be like tumbleweeds and like
Right,
stuff?
right.
But Tucson's a pretty cool city. So it's
Okay.
been nice.
And where are
Yeah.
you originally from?
I'm from the LA area, but I've been
Okay.
in California my whole life. Yeah.
Okay. That's cool. That's cool.
And what about you,
Nice.
Phoenix?
So originally I'm from Maryland. I grew up in Baltimore County, and then I moved to the
Mhm.
city when I was about 16, and then
Yeah.
I came to Ohio for undergrad. So
I feel like that's a big switch from Columbus to
it
that.
is. It is. It's like being DMV area. It's so different versus being Midwestern. Low key,
Yeah.
I still miss home. I get homesick, and it's like all the good seafood is in Maryland, the blue crabs and everything. I don't have access to that here. So,
Feel that.
so originally, how did you become involved in astronomy?
So I I guess outside of like academia, I would say
Hmm.
like mainly just watching like PBS and stuff. Like there isn't a ton of dark sky where I'm from, so it's mainly from like what I've seen on the TV. And
Right.
I was like, okay, some of these missions to go explore the outer planets seem really cool, and that's how my interest sparked. But in terms of like academic research, it was summer research. And my first like impactful research experience was at, NASA Goddard. And I had a really good mentor, Aki Roberge, and I really had the chance to, find ownership of this project and think about the interpretations. And it was about debris disk. And I was like, okay, I can maybe do the science thing. So
Right.
yeah.
That's
that was-
good. Yeah, I feel like a lot of people, especially my generation, their gateway is like Bill Nye the Science Guy or Neil
Yeah.
deGrasse Tyson, and then kind of
Mhm.
builds from there. But I also relate to that.
Yeah. Well, I guess now that like, you know, you have a lot more colleagues who are astronomers who write about their experiences. So
Hmm.
I feel like it's nice to have a broader perspective nowadays.
That's
Like,
true.
I'm not sure, have you read Disordered Cosmos by John
I
Estelle Einstein?
I have not.
I would say that if I had read that when I was like really young, I would have been full sold. Yeah. Yeah. I like having someone say like you have the right to curiosity. Yeah,
Yes.
like out the gate. It's pretty
Yes.
cool.
Yes. But that's nice. And kind of briefly, what is the focus on your research?
Sorry. So currently, I mainly work on brown dwarfs. They're these substellar objects, and they're cold enough where they have all these cool molecules in their atmospheres in the gas phase or cloud phase. And so I use spectroscopy to, disentangle, what is the exact chemical composition of the molecules in their atmospheres. And outside of that, I also work on instrumentation. So I've been in graduate school, I've done some detector characterization work. Now I'm a little more interested in trying to propose new instruments and figure out how to do that too.
Nice. That's really
Yeah.
cool. How long have you been in instrumentation for?
I would say probably 4 years now is something I
Okay.
started at the end of grad school. Yeah.
Got you. Do you like being hands-on and building different instruments, you would say?
Yeah, I like to build things uh outside of work too. So like I built the computer I'm using right now.
Oh,
And
wow.
so it's really rewarding to like see something like you thought of and you thought all the parts and it comes together. Yeah.
Nice. Nice. And then for those who you kind of described it a little bit earlier, but for those who may not really be familiar with an astronomy and astrophysics, what exactly would you describe a brown dwarf?
So I would describe a brown dwarf as like a really large Jupiter-like object.
Hmm.
I a lot of people their context to brown dwarfs is like they call it like a failed star, but that's not exactly accurate.
Mm.
It's just not big enough to fuse hydrogen like other stars,
Right.
but it's mainly a hydrogen helium atmosphere with other molecules thrown in there as well.
Mm.
And in terms of like physical scales, it could be anywhere from like 70 Jupiter masses to like a Jupiter-sized object. And so, yeah, I think they're pretty cool.
Nice. And so, do you know how originally brown dwarfs were discovered and why were astronomers interested in them initially?
So, to my understanding, brown dwarfs were theorized very long before they were actually seen.
Hmm.
So, I guess back in the day, people were like, okay, we have all these stars and we know that low mass stars exist. What's the smallest thing that can just condense out of an interstellar cloud and still fuse hydrogen? What is that thing going to look like? And
Right.
so people theorized that they would be like, brown dwarfs, they would be really bright in the infrared. And
Hmm.
so there's two ways you can find a brown dwarf, but the first discovery was an actual companion next to a bright star. And so if you take pictures and multiple filters, you can figure out, okay, this thing is more brown dwarf-like and too cold.
Mm.
And it's probably doesn't fuse hydrogen, it's probably a brown dwarf. And so that was like how Gliese 229 b was discovered.
Mm.
The other brown dwarfs were found through these really wide field infrared surveys. And so brown dwarfs are relatively close to us. And so they have a pretty large parallax. So if you take two pictures several months apart, it will move very quickly relative to the background. And so if it's also very dim, that tells you that object's very cold. And because of things like the two mass survey and also WISE, which was done from space, we have kind of filled in this gap between the lowest mass stars and things that are maybe around the temperature of Jupiter.
Hmm.
Yeah.
And so, do you know why so much we compare brown dwarfs mass to Jupiter? They're just kind of similar within that regime, and that's the closest approximation that we can get.
So that's a good question. We compare them because I talked about the mass a lot, but most brown dwarfs are around the same physical size as Jupiter.
Hmm.
Um, and also, like, I know Jupiter, a lot of people say, like, Jupiter is in the solar system, brown dwarfs are floating free or around another star, so they're totally different. But there's actually a lot of overlap in this type of science or the required atmospheric chemistry and physics you need to understand to comprehend their atmospheres.
Hmm.
So in that regard, a lot of the coldest brown dwarfs are really good analogs to Jupiter or like the coldest planets we can take pictures of right now. And so I think they probably form in different ways, but the observables we can measure right now, they look very similar. And so that's why we
Hmm.
compare them. Yeah.
Got you. Got you. And I know sometimes a lot of astronomers, they'll be like, oh, this planet or this brown dwarf may have formed more so like a low mass star and a high mass
Mhm.
planet. And so how does a brown dwarf different from a star or a planet?
Got you. I think anyone who is like, they know the answer to that, I don't think we know the full answer right now. If
Right.
something formed like, if something is a very wide companion from their star, like we're talking about hundreds of AU out, maybe it formed more in like a cloud and then came together with a primary. Um, for things that are really massive and close, I think we're still trying to understand, are there signatures that tell you, did this planet form with more of a core and then it developed an envelope,
Mm.
versus something that is enriched with whatever it has when it was born out of an interstellar cloud.
Right.
Um, I would say we are still trying to understand what is the internal structure of Jupiter and Saturn. And so there's still debate on if there's a distinct core in the planets in our own gas giants.
Mm.
There may be some enrichment from like little planetesimals or comets that would be apparent on something that is in a system rather than isolated. But we're still trying to figure out what is the like, you know, the actual signature that will tell us this formed like more of a planet than a star. A
Right.
lot of people will say it's deuterium, but there are brown dwarfs that are free floating, doing their own thing that are below 13
Yes.
Jupiter masses. And
Yes.
so I think that is not, I think it's a diagnostic. It is not the final say on formation.
Mm.
Yeah.
Thank you. Yeah, I think also there's a lot of data being collected through JWST and as hope open a lot of possibilities to look at different brown dwarfs and their
Yeah.
future as well. And so with that, like what do you think are the next big questions in brown dwarf research and how are the newly released data from JWST contributing to the understanding of brown dwarfs?
That's you. I would say so we're still in the awkward phase where people are still struggling to model the data.
Mm-hmm.
So I feel like every spectrum is just like, wow, I didn't know that before. So one surprise that we're finding as a community is that like brown dwarfs, even though they're similar temperatures, can look very weird or different from each other or can show different features. And we need to understand like, okay, is this an extra parameter we need to turn to cause this diversity, or do we need to revisit our assumed chemistry?
Right.
The other thing that I would say we are is a continuation of like previous work from like Spitzer and Hubble is like actually being able to measure clouds in these atmospheres. So one thing with Spitzer has really low resolution, but had really low signals to noise.
Mm,
And so, but with MIRI, you can maybe say like, we detected this silicate cloud. It has this grain distribution. It's this high in the atmosphere, and go from there, or say what type of crystals the silicates are made of. And on the colder end, there may be water clouds that can form in white dwarfs. And so
mm,
understanding how water clouds exist outside of something like Earth is also
mm,
something we can start probing with JWST.
mm.
Yeah.
Cool. Thank you. And like, what is your current contributions within Brown Dwarf research? What you say, and then what is the main research goal, and how will it help aid an overall understanding of brown dwarfs as we know it?
I would say my biggest contribution to the field has been um, one, measuring disequilibrium chemistry and
Mm-hmm.
actually understanding based on this, like carbon monoxide, essentially, based on this measurement, how how quickly is the atmosphere overturning due to convection? And
Mm,
so this convection brings up warm gas from deep in the atmosphere to the top where we can measure it, and it changes the apparent chemistry we can see. And so I've been doing this work since pre-JWC, and some of my early work showed that colder brown dwarfs and planets probably have stronger mixing in their atmospheres, whereas the warmer brown dwarfs probably um, have some sort of combination of radiative and convective zones that make a mixing less efficient.
mm,
And so, people have theorized this before, but I had the data to show it. And now with my old project was done with Gemini North at like a resolution of like 50 at best, whereas JWST, we can start making these measurements at signal to noise of 100 at a resolution of like 1,000. So by adding resolution elements, you can probe more of the pressure temperature profile and maybe start saying, oh, instead of this atmosphere is mixing, I can say it's mixing this much at this pressure.
mm.
And so by understanding how much the overturning is happening at a given pressure, you can maybe make predictions on the type of chemistry you can see. And I
Nice.
think I have two programs that continue that work with JWST, and I think they'll add a lot of insight into how the chemistry we see is tied to the actual structure of the planet or the brown
Nice.
dwarf.
That's interesting. Yeah, I've never really worked with GWSC data before, but I've worked with like Specs Prism,
Mhm,
and trying to do spectra analysis as well and reanalyzing intermediate mass brown dwarfs. So it's really nice to have different perspectives as well.
mhm. And
And oh,
oh,
sorry, please go ahead.
I was gonna ask because I think Specs is a really good instrument, and like
Hmm.
it's so many brown dwarfs have been probed with it, and it's such a like standard. I guess, are you interested in like larger scale comparative studies, or are you focused on a few objects?
So the one I'm looking at right now is just one specific intermediate mass brown dwarf. And I
Mhm,
think it was first discovered about 12 years ago, but since it's an
mhm.
intermediate mass regime, its formation mechanism is more uncertain. So that's
Yeah,
why we're reanalyzing the object. So I worked with
nice,
Specs Prism, XSD, and Kekosiris.
nice.
Yeah,
That's awesome.
thank you. And just kind of to wrap it up, can you share a memorable moment or discovery from your career?
Got you. So I have a few, but I
Mhm.
think my well, the JWST related one was with the ERS program, the early release science program. There are a few teams selected to, do early science from the observatory to make sure it can basically do what they said it would do. Um, and so uh, our team decided to look at this object VHS 1256b, and so it's a fairly widely separated brown dwarf that is very similar to like the HR 8799 planets, which is like the usually the first system people think of when you think about like a directly imaged planet, which has four
Mm.
Jupiters, and there are about 1400 to 1200 Kelvin objects in that system. And so we took a spectrum from one to about we took data from 1 to 28 microns. It's about 1 to 20 microns. And so uh, when JWST was launched, the pipeline was in very early stages, and so it was a struggle to like get the spectrum to look like something.
Right.
And also the JWST pipeline would run so slow. So I
Hmm.
remember my favorite discovery, I was like at home, and like it was when I saw like the carbon monoxide feature at like 4.5 micron, and you can see like
Mm.
the P, Q, and R branch beautifully, and it looked
Hmm.
just like theory. And like since I was waiting for the data to run, so the pipeline used to take like an hour to run. And
Hmm.
so I would play games in it. So if I was logged in a game, I would tell everyone I'm gaming with about like these features, and they're like, okay, what is this? What is this person going on about? It was just so like the fact that we can get data that looks like laboratory data is like
Yes.
wild on a brown dwarf. We're finally like in the future, and it was now. And yeah, I'm sitting up on my computer at night just so hyped.
Yeah.
They'd be happy. Yeah.
Yeah, I think JWSC it was launched when I was still in high school, and then once the
Mhm.
pictures came out, it was just really a starstruck moment for me and just seeing the different things. And it's like at the time I didn't fully understand everything
Yeah.
as I did now, but I was like, it's just very beautiful pictures to look at. And also, where the neighborhood I worked at was also the same neighborhood as the Space Telescope Science
Yeah.
Institute. So like just riding by on the bus, I'd be like, ooh, that could be me one day. So that's
Yeah.
yeah, yeah.
Wait, so how was it for you in high school? Okay, and in high school, were you certain about
Oh.
astronomy, or were you
Yeah,
like,
so I've always really had an interest in astronomy. So
yeah,
when I was probably elementary school, my mom, she bought me like a telescope, and you couldn't really see anything out of it, but it was still the
mhm,
principle of it.
yeah,
And then she would take me to like the Maryland Science Center, and then she would buy me like different science books. And so I didn't really know, or I didn't take it as seriously as astronomy until 10th grade. And that's when
hmm,
COVID hit. So like during that
yeah,
entire, like during the day, I would just look at different colleges like, oh, I can go here and possibly and stuff. So originally in my
hmm,
mind, I had like so I was so set on I was like, I want to go to University of Toronto for
yeah,
undergrad for astronomy and astrophysics. And then kind of I opened up my perspective. And because of the COVID at the time, I was like, okay, let me just kind of stay here in the US.
yeah,
So I applied everywhere. And then I ultimately decided on Ohio State. But
mhm.
originally, I kind of had like pipelines of like maybe criminology or culinary or even journalism.
Nice.
So
That's awesome. And
yeah.
I'm glad you made it through.
Nice to meet you as well, and hopefully we can keep in contact in the future.
Absolutely.
Okay, thank you so much. It was great meeting you.